Thank you for joining us again. And my name is Berk Üstündağ, and I'm the Vice President of International Society of Agrometrics, ISEM. And today we are welcoming you to the first or third session of Agrometrics webinar series. And today's webinar is entitled as Near Real-Time Data Analytics in Agriculture. We are going to be exploring the usage, effectiveness, and the trends in near real-time data analytics for agriculture. And I'm really delighted that we have valuable participants this week again in today's webinar from academia and the community of agriculture. First of all, I suggest again non-ISEM participants member participants to be registered to ISEM through www.agrometrics.org so that they can be informed about activities of the agrometrics community and take ISEM's other future benefits. And now, please keep your microphones muted. Questions may be asked anytime by utilizing the chat function, and they will be answered by the end of the session. We have a distinguished speaker today. I'll take this opportunity to introduce you, Professor Vladimir Crnojević. Welcome, Professor Vladimir Crnojević.
Thank you.
Professor Crnojević, can you hear me?
Yes, I can hear you. Do you hear me?
Yes, I can. Well, it's very nice to hear you.
Good, good, good.
So, Professor Crnojević is the founder and the director of the Biosense Institute. And Biosense Institute is an R&D institute for information technology in biosystems with application of micro and nanotechnology sensors, Internet of Things, robotics, remote sensing, artificial intelligence, and various biofields with special interest in digital agriculture. And Professor Crnojević is also a full professor in computer science at University of Novi Sad, Serbia, and he has the expertise in image processing, machine learning, and many other fields. And under his leadership, Biosense Institute became recognized as a regional leader in digital transformation of agriculture with more than 100 various implemented projects, and many of these projects are from European Horizon 2020 program, including flagship projects such as Antares IOF 2020, which is Internet Food and Farm for 2020, and Smart Agri Hubs and so on. So, as you commonly know, data has an increasing role in agricultural production and management due to the rising importance of yield, efficiency, and the sustainability. And precision agriculture and good agricultural practices are based on evaluating various types of the data and the knowledge. And recent developments in communication, data processing, and sensor technologies are expected to provide several game-changing applications in agriculture. So cloud-based services enable high-performance computational platforms and reliable data processing capabilities in cost-efficient ways to users connected through mobile applications, web services, or machine-to-machine M2M communication interfaces. And near real-time data analytics for timely and accurate management applications in agriculture will be evaluated and presented in this webinar by Professor Crnojević. You are welcome, and thank you for your coming here, Professor Crnojević. Now.
Thank you, Berk, for the invitation and giving me the opportunity to present our view at the problem of digital agriculture and to present our activities that we are working on. So at this moment, I will share my screen and go through the presentation. You should enable me to share.
Yes, I have already enabled, and you can share your screen.
Okay, fantastic. Let me get it from here. I guess that this is it. Good. Do you see it now as a full screen?
Yes, we can clearly see that.
Okay, good. So hello, everyone. I have prepared a few hundreds of slides. I'm joking, but it will be presentation, a quick one. I will try to cover as many topics and activities as possible. The point is that we are really going to present something that is the result of near real time. When we say near real time, it's either immediate analysis or action, or with some minor delay. And I will not focus on AI too much, because it's becoming plug and play thing today, but the problem is of getting the data, preparing the data, and providing the action in real time. So let's go through that. First, we like to portray this as a future, to have a digital village where we have different aspects like monitoring of crops, disease detection, forecasts, satellite images, and other things that are helping us to manage the village of the future in a sustainable way and provide enough food for the growing population. So in order to provide this concept and make it viable in the future, of course, the whole thing is going to be relied on data, as all of the aspects of our life are getting more and more related and relying on data analytics. So in our view of the future of agriculture, basically we are using in an opportunistic way data that we can get from various sources, some that you have in mind immediately, like soil moisture sensor, weather stations, satellites, but also robotics is getting more and more into agriculture. But also there are some other things like mobile phones, telecom networks, and other stuff that are becoming tools in everyday agriculture. So it's getting really interesting to see how things will be developed in the future. Just a few words about Biosense Institute. Berg has already mentioned that we are R&D Institute for Information Technology in Biosystems. So a quite wide field of merging of IT and bio. But what we focused on is agri-food, and like 80% of our activities are related to agriculture. We were established 7 years ago, but we are already almost 150 people and a number of associates from the side. The biggest project is Antares, where we were by European Commission, we were selected as #1 center of excellence out of 170 centers, with the special focus on agri-food. Kind of structure of the institute is not only administrative, but it is good for the illustration of what we are talking about today. So as I like to point, we have 5 centers. 3 of them are research centers. So at the bottom is the research center for biosystems. So these are domain people, agronomists, molecular biologists, and other ones who are providing the data. But this data, these phenomena measurements have to be converted to data and delivered to the center on the top, which is the Research Center for Information Technology. So these are guys that are crunching the data. But in between, it's the critical point, as we see, it's the Center for Sensing Technologies. So these are people who are converting the biophenomenon into data and provide data analytics in the future. So in order to do that, we are just finalizing the construction of the new building of the Institute. But what is interesting in a structure is that we have the floating core of the building that is detached from everything else, and it's under in the clean rooms of high accuracy and with special requirements for clean technology. We are able to go into nano worlds where we see the future for many sensory systems, but also notably for agriculture. Our vision is to go through development of biosensors that will provide us to measure various phenomena that will really provide the data analytics with the needed data of being able to measure different things, both from biochemistry and physical world. So this is just a few things to illustrate where we are going. But if we look at the broad picture, this is the vision that we have foreseen for the future of agriculture. So starting from the farmer with regular tools and notebook to take the data and really do the manual analytics, we are going into the world where every piece of this puzzle is becoming the source of data. So we have the plants that today, through automated phenotyping and DNA analysis, are giving us much more information that than compared to something that was possible a few decades ago. Availability of various sensors are providing us with the opportunity to measure a number of parameters, both from soil, plants, animals, and giving us the possibility to really treat this as one integrated data system. So I will present a number of these examples in my talk today, but also we have, apart from measuring the phenomena on the living things, we are also getting the data from the machines today that we really, they're getting smarter and smarter every day. And John Deere has announced a few months ago that they have collected by now from their machines more data than Twitter. So you can imagine what is this asset in the future. So from different tractors, harvesters, and everything else, we are harvesting the data from their sensors and giving the possibility to go into data-based agriculture in the future. So when we speak about smart machines, of course, the robotics is having exponential growth in agriculture. And just recently, also John Deere has launched first fully autonomous machine that doesn't need human assistance. A kind of robots are also drones that, let me remind you that first drones with 4 propellers were presented in 2012, so only 10 years ago. Nowadays, they became regular tool in agriculture, and nobody is even referring to them as something new. Also, it's worth mentioning the satellite technology that is providing us with more and more frequent data and really getting us there to have almost real-time analytics possibility. So as we know, from Copernicus service Sentinel data, we are having them now every 3 days, but also Planet and other commercial providers are giving us the possibility to have daily delivery of data. Also, in order to have a wide deployment of the sensors that we have mentioned, we have to rely on IoT systems to transmit the data from the domain, from the fields and barns. And it's also worth mentioning that in order to feed the growing population, which we have just turned 8 billion, and we want to live longer and longer, we have to take care of biosystem that we are living in, and it should be integral part of this, and it also requires data analytics possibility. So in the end, of course, everything goes into what we like to refer as a cloud, and to give us the possibility to use state-of-the-art artificial intelligence tools in order to, in the end, deliver services to the end user. Speaking of end user, here it's portrayed as a farmer, but today it's all integrated digital system. So we have not only farmers, but government, banks, insurance companies, processing industry, logistics, all of them are integrated into one big data system. And this is the big picture that we are talking about. So in the next slides, I will take you through bits and pieces that are shown here on the picture. Just a few mentioning them. We mentioned the satellite revolution that we are going on. Every day we have new satellites being launched, which are giving us the possibility to really have in near real time data. As I said, this is the Sentinel image they're giving us the possibility through NDVI or SAR to monitor every 3 days what is going on. But also drones are giving us the possibility to have very, very high resolution maps on an arbitrary frequency. And this gives us this possibility not only to recognize what is going on the fields, but also to see the condition and to measure on a daily level the progress and the potential problems of the crops. Also, it's worth mentioning that sensors, as I said, that are having the important role in the future for real-time data analytics are getting more and more interesting in the biodomain, and also mobile phone is now it became the extension of our hand. We are using it for many things, and also it became the tool in agriculture. If you add the additional sensors like thermal cameras and spectrometers, it's really becoming a powerful tool for agriculture. So let's start with a talk on infrastructure to collect the real-time data. We call it in much wider framework as Internet of Things that is foreseen as a future in different domains. But first thing that people are having in mind is urban areas. We have the problem here to cover the rural areas and to really be able to connect various sensors into this system. So today we have a number of different competing technologies that have their advantages and disadvantages. And in our example, we are using LoRa system to provide the connectivity of sensors in rural areas. Basically, this gives us the opportunity to connect a number of data gathering devices into a wide network that is transmitting the data in real time to servers for further analytics. So we have the possibility here with LoRa to have relatively low-cost system with two-way communication that can be done with a public network, but also to be implemented as a private network. What we have as a project in Serbia is to work together with the national telecom provider to be complementary provider of rural areas. So they are covering the urban areas, but didn't have much interest for rural areas. And we are putting our gateways into their network. And with a distance of 15 kilometers and low power consumption, we have the possibility to connect a number of sensors at the LoRa nodes that we are currently using. So the other technology that is foreseen as a competitor to LoRa is narrowband IoT, but it has its advantages and disadvantages. The deeper penetration, easy deployment, long battery life, and relative low cost. But the point is that we have the possibility with LoRa to implement private networks and to give the here, as you can see, in this domain, that cost efficiency and deployment is battery life is on the side of LoRa system, where we can deploy private network, and we don't have to rely on the standards and protocols that are, let's say, designed by the public institutions. In our case, we are working with LoRa and also providing the customers to use their gateways. So big companies are taking the gateways and putting their own private networks for sensors. So this is just a few words, a few slides about the infrastructure. And now let's go to some details of the implementation of a number of problems that we are using. So one interesting project that we were doing with Strathclyde University in Glasgow was the behavior of cattle, to monitor the cattle behavior in order to improve the production of milk. So in UK, number of milk producers is decreasing, and the average farm size is increasing. So also the milk production is increasing, and it makes less time for farmers. So automation is necessary in order to provide rich data environment to provide a further growth of the milk business. So to increase the productivity, it has to be done in two ways. One is improvement in genetics, but also the other one is adoption of digital agriculture technologies. So there are a number of existing solutions currently on the market that were developed from various perspectives. The point is to have the monitoring of rumination, eating, and other phenomena. And what animal scientists are interested in is heat detection, calving, and illness detection. So it turned out that by behavior of the cattle, physical behavior, we can detect many of these phenomena through data analytics in almost real time. So in this case, we had the collars on the neck with accelerometers and temperature sensors. But there are a number of devices appearing on the market with other concepts. Basically, those are all sensors connected to the network. So in this case, there was a trial on 3 farms with many hours of monitoring, and two sensors attached to the neck and muzzle, where they were sending the signals to the data analytics system for classification, for analytics and classification of the behavior of the cow. So in a certain moment, when they start to move the neck in a particular fashion, then it's a strong signal that they're in heat, and the insemination it's a right moment for insemination. Usually that would happen by a farmer that would or a shepherd that would look how the cow is behaving. But with these sensors, it's much faster, and with advanced data analytics, we were able to detect even a few days in advance before it became obvious to the farmer. So this is one interesting example of data collecting in animal farming, and there are others that are appearing every day. Now let's see the same infrastructure for data collection, but in other domain, in soil moisture. I just wanted to mention here that we have our own development of number of sensors, and this is our solution that has been patented as a soil moisture sensor that is a real plug and play sensor. So it's quite cheap. it's not based on the conventional technologies like capacity or resistance, but on phase shift method that is immune to noise, and it doesn't have the influence on soil electrical conductivity. So it's much more independent from soil type, and it's really give us the possibility to use it in IoT concept with long-lasting operation. So this is the illustration of operating frequency influence for different salinity. So distilled water in one case, salinity 29 and salinity 70, and you can see the response of the sensor. But what is interesting that this is the regular on 500 megahertz that you would see in other solution, but in this case we have basically the clear measurement with without the effect of salinity with the newly proposed solution, and currently it's been prepared for the market solution as a plug and play device where you can use it in various soil types. So compared with the most widespread decagon sensors, it shows that for different soil types, it's much more robust, and it doesn't need to have the complicated calibration. So the idea here is to use the current soil moisture sensing technology together with the other data and to go with soil moisture prediction. Why is this important? So in currently the water resources are getting critical. I can tell you by our area, currently we are in January and we don't have any sign of snow here, which is common for January, which clearly shows us that in summer there will be huge problem with the drought. And the previous summer in 2022 was really critical. We had yields of 30 to 40% of what would be a regular yield. So irrigation is of paramount importance, but in order to optimize the resources, we have to develop the system based on real-time data to predict not the weather, but the soil moisture in few days in advance. So in our case, we have developed interesting concept. We have our own weather stations that we have deployed over the area of Serbia where we live. And we have 500 weather stations that are measuring weather phenomena, but also, as I said, through LoRa network, we have attached a number of soil moisture and soil temperature sensors. On the other hand, we are using open source data sets from Copernicus Climate Change Service. ERA 5 climate data with spatial resolution of 0.25 degrees and hourly tempo resolution is giving us the possibility from its historical data that we can provide the prediction of average data daily values of volumetric soil moisture so for 3 days ahead in the layer of 7 to 28 centimeters. And this is the problem of time series prediction. If we get air temperature and humidity along with precipitation, we can go into prediction. So the problem is to predict the time series, and in this we are in this complete problem. We are using neural network with 4 LSTM blocks and 40 neurons, and we are providing 60 daily values of maximum air temperature, minimum air temperature, precipitation, vapor pressure deficit. And this is what we have. So basically, by using yr.no with Norwegian Meteo Service, which I believe many people are familiar with, using Copernicus historical services and neural network, along with the measurements from our sensors, we managed to develop the 3-day prediction of soil behavior based on the weather forecast. So, and for different soil textures, these are 4 different parts of the country with 4 different types of soil. And you can see that by using ERA 5 data from Copernicus service, we managed to develop the quite good prediction of soil moisture 3 days in advance. So this gives us the possibility to operate the irrigation system in a smart way. So if the weather forecast says that it will not rain, but our soil prediction system tells us that there is enough water capacity in the soil in the next 3 days, we don't have to irrigate. And by using this, it has been verified already. By using this, we managed to achieve huge savings in water for irrigation by reducing the amount based on this So speaking of sensors, another development of ours, but in different domain, this is optical multispectral sensor that is resembling the Wall-E robot from the Pixar cartoon, is called plantometer. And it's basically, it's been developed as an idea to use in the beginning 4 frequencies emitted from one lens and the reflection captured in the second lens. And in current version that is on the market already, we have 6 different spectral wavelengths and the possibility to use this device in a number of ways to provide the real-time measurements of plant condition. So on the right-hand side, you can see the mobile phone picture from the screen of the mobile phone about the dense measurements of the plantometer that is mounted on the tractor or robot and going through the rows of plants. And it gives us the possibility to measure more than 15 physiological parameters and connect directly to the mobile phone and the network. So this is real-time data uploaded into the data analytics system. So it can be used both manually from the hand, mounted on the console, but also on tractor, robots, and many other things. This device is really it's proven to be very useful for calibration of other data that we are using from drones and from satellites, because we have really proximal measurements of the plant condition. And also, speaking of using this device in automated way, one of our important activities for collection of real-time data, but also providing real-time action based on this data, is in robotics, where we are using different robotic platforms, not only to carry plantometer, but also to do different sensing and actuation activities like soil analysis and spraying of plants. So this is a concept that we have developed as a lab on the field to provide real-time soil analysis. So currently, if you want to do the soil analysis, which is important for any activity and treatment of plants, usually farmers take the sample with a drill and they do it uniformly across the field, and then they take it to the lab and wait a few days or even weeks to get the result back, and then to get the recommendation from the expert. Our idea was to develop the methodology to really use the robot to measure within the time frame of 25 to 30 minutes to do the analysis on the go. So while it's moving from one point to another point, it is doing the analysis, and it's connected with the mobile platform operator, farmer, and different data systems to be for analytics of not only the soil data, but together with other sources like satellites or drones. So the idea is to let the robot go into the field to collect the data, to collect the soil samples, do the analytics on the go, and let me just play the video for you. So the idea how we develop this is that there is a drill on the robot that is pulling up the sample from the soil and doing the analytics by mixing with waters the necessary chemicals to isolate the nitrogen content. There is a mixer and drainer, and everything is inside. And as I said, we have come to possibility to provide the real-time analytics of data. This has been applied in Flexi robots project, where we have the name of the project is Flexible Robots for Intelligent Automation of Precision Agriculture Operations. So it's doing the detection, the assessment, and the action in the end. And we had a number of use cases where from monitoring, sampling, detection, and spraying, the whole system has been developed through robotic procedure. Just take the water. So first of all, monitoring is done by something that we have already mentioned. Those are weather stations and soil moisture sensors. Also, we are using not only satellites by drones. We have to say that we have really rare opportunity to use Trinity F90 Plus satellite, UAV with wide coverage. And this is equipped with 2 multispectral cameras. So totally, it's 2 microsens with total of 10 spectral bands that we developed. And based on this data, we are sending the robot to do the drone analysis. So as we presented already, from one to one point, it's already analyzing and sending the data up. So based on the scanning of the by the sensor EM38, we can choose how to choose the sensing points, sampling points. And based on this, we can do not only measurement of the condition of the plant but also the detection of diseases, which is obvious in here picture, but it can be detected with a number of sensors. So we can use multispectral UAV images to get various vegetation indices, and by deep learning or other data analytics method, we can develop segmentation and sampling. Also, today, hyperspectral cameras are becoming more and more approachable. Currently, something that has been tens or hundreds of thousands of dollars is getting to much more approachable level, and we have the possibility to use this together with the gimbals and state-of-the-art drones to get multi and hyperspectral indexes in various images and use data analytics to derive the critical important data from this. So not only to use drones for vegetation indexes, but also to have a huge palette of analysis without the possibility of some effects like hail nets or other stuff. And of course, with respect to data analytics, we have to mention the state-of-the-art algorithms. Of course, deep learning is dominating today the world in a number of aspects. This also holds for agriculture. But we can tell that genetic algorithms are still there, random algorithms like random forest and other techniques are present in our everyday practice, and we are using it for image segmentation, pattern recognition, behavior of animals, and many other things. So in this case, we are demonstrating the road detection by data analytics that then we can use not only to estimate the condition and the yield, but also for clustering of the plants and design of a strategy of treatment on different parts of the plants of the field. So in this case, this is a project Flexig Robots, where we are treating the blueberry rows by this fusion of multiple sources and coming out with a strategy where to do which treatment in which part of the fields, both from the point of view of spraying, but also selective harvesting and many other things. And speaking of UGV spraying, also we have the development of automated spraying from blueberries within the same projects to have the horizontal and vertical folding boom with the sprayers that can provide the robot to go through the lines and do adaptive spraying in a smart manner, also with the feedback on the results of spraying. And this is the concept where we are talking about the coming back to the beginning. We are going into digital village direction, where by collecting the crop monitoring data, early disease detection, meteorological forecasts, changes in production parameters, soil parameters, satellite and drone images, and do the data analytics by state-of-the-art algorithms that we are having today in the cloud, and delivering this in real time to different stakeholders, we are really coming to the possibility of developing the near real-time data analytics in agriculture. So we are working with huge number of farmers, individual farmers, tens of thousands in Serbia, but also we are working for different insurance companies, bank companies, and big agricultural companies, with providing them with infrastructure and data analytics. For this, just to give you one example of near real-time practical commercial application. So we have Generali insurance company present in Serbia. And of course, the most critical peril is the hailstorm. And what they have seen, they have noticed that in some cases, farmers are waiting for the hail to happen, and then they go and report and buy the insurance after the hail. Why? Because the insurance company has the methodology to go out in the field 7 days after the reported hail. They want the plants to settle down and to have the real to have the possibility to really evaluate the real effectiveness. But they have noticed that farmers are fooling them by buying the insurance immediately after the hail and then reporting 2 days later. So we have developed the real-time system with European Weather Service and the Space Agency. So if there is we detect the hail clouds and the high incidence of hail, we lock the sales of insurance on the given territory for 48 or 72 hours, depending of the parameters. So in this way, we have provided the insurance companies with huge savings and closing the gap for misuse and manipulation of this. And of course, you have to have the near real-time data for this. There are a number of other things that we are using, like giving the farmers the real-time information about the condition of the crop and the necessity for treatments and weather parameters, to give them the possibility in an automated way through their mobile phones or other means of communication, to give them the strategy, the plant treatment and soil treatment in the forthcoming few days. So I will maybe stop here to have some times for discussion. I think that we are within the time frame. Thank you.
Thank you, Professor Vladimir. It was a nice, attractive presentation, and you always are having creative solutions in the way we commonly think about the things to be solved, and they are quite vital issues for the forthcoming decade about agricultural production. So we may have questions from the participants or their remarks, comments. You may text through the chat option here. And meanwhile, first of all, I would like to ask the correlation about the hail prediction so that it can be recognized as an official decision, as a threshold for accepting the insurance applications within that time interval.
Well, we have the probability of the incidence of hail that we are getting from EUMETSAT by I think every 15 minutes we are getting the cloud map. And if it's going above the 90% of the incidence of hail, we are displaying this on the map, and we make the alert to the insurance company to immediately lock the sales in order to close the gap for possible manipulation. Because like everywhere, in every country, in insurance, agriculture insurance, basically the hail is the #1 problem and #1 product for insurance, because everything else is lacking enough models and enough data, and insurance companies are staying away from that for the time being.
So the forecast time interval is something like half an hour, or a day for 90%?
I have to check. I think every 15 minutes we are getting the updated information in the clouds from EUMETSAT, and then based on that and other parameters that we are collecting, we are making the decision of the strategy of sales of the policy for hail.
Yeah. And the soil moisture is the most critical measurement, probably, from the soil for yield prediction and also the irrigation management. So there are hundreds of parameters, but the #1 is probably the soil moisture. So you really refer to mainly nowcasting of the soil moisture, because you may not have sensors everywhere, but you may have some sensors, some reference points, as we were targeting that similar strategy in Tarbil, in Turkey, as you know. And but the sensors were really the most problematic the issues by themselves because of their calibration, sensitivity, and one of the major problems were they were being affected by the salinity of the soil because of the methodology that they are using. But if you have really introduced these microwave sensors in a reasonable within a reasonable cost, then it is a great advantage, and we may even use the same sensor at multiple depths of the soil, such as 15 centimeters, 50 centimeters, and so on. So how do you compare them in terms of their applicability? Because once you embed the sensor, you have to take care about some, for example, a few weeks so that it can establish the coverage between its surrounding environment in the soil condition. And have you also compared the accuracy of the sensor with respect to other physical methods such as lysimeter, where you measure exact soil water content in the lab condition? So what is the accuracy and the type of applicability as you may propose us?
So we have compared the performance of the sensor with respect to accuracy. It's on par with something that you have on the market, like Decagon, which is probably the most sold, or Watermark. But as I said, the point is that it's working on microwave principle on 2.2 gigahertz, which is the frequency that we have found to be the most stable from the point of view of salinity and the soil type. And it's really plug and play sensor. We have a patent on that, and it is currently we have the licensing agreement with Watermark, which is the biggest soil moisture sensor producer in the world. If everything goes well, it should appear on the market in the next few years. And it gives us the possibility to really go beyond current problems that you mentioned, which really takes a lot of effort to do the proper calibration and to get reliable measurements. And also from the point of view of cost, this should be really low-cost device that would give us the opportunity to go from currently $100 per sensor to go into much less than that.
And what is the power consumption range? Will it be able to be powered through a battery for a long time by having it in standby condition outside the measurement periods?
Yes, it is foreseen to be in IoT system where it cannot use much of the resources, but also we are also counting on solar panels that are on the gateway to support the extended battery life.
And Serdar, you would have a question, I guess. I have seen your hand raised up.
Yeah, I am Serdar. I have a question, and actually it's going to be more. How do you make your system useful to farmers? How would you expect them to use it and actually take your decision for grant and actually, for example, use your advices? And if something happens, are you responsible for that? Like, I don't know, you predicted the wrong thing and things happen. So
Yes.
So you can look it in two ways. First, how do you make it usable so people can access it and really make it a fruitful source of data and act accordingly? And second, if you make any predictions, do you feel any kind of obligation to the farmers?
Yes, thank you for the question. What I didn't present now, we have many other activities. One of them is so-called AgroSense system that we have developed as the open source platform for farmers for free. Anyone can go there and register with one email address and use it as a tool where we are adding all state-of-the-art things into the system, and some things that I have presented here are also there. We give some recommendations, but of course we don't take the responsibility. We leave it to the agronomists. And in our platform, there is a matchmaking part, which is giving the possibility for agronomists to use our technology and our measurements to give the advices to their customers that are in the same digital system. So it's e-agronomist that is giving the recommendation to the farmer based on what we are providing. So just to give you one example, based on the analytics from the satellite images, we are giving for free the farmers the soil structure map so that they can do the soil sampling in a smart way and get the recommendation for fertilizers, not to have the uniform application. And it proved to be huge advantage for farmers. So this is obvious that we are not putting them in any danger or problematic situation by giving them smart strategy where to take the soil samples. And this is the free service that they can use for their own benefit. And all these things are within AgroSense system for free, with explanation how the tools should be used. But of course, we are there to provide advices for individual farmers on non-commercial basis. For big companies, we are charging, but we are developing custom-made systems for their needs together with their experts.
Thank you.
Thank you. Is there any other question?
Omer is there.
I have also another question as a part of my previous question. Have you ever compared results about measurement device for the soil moisture to the lysimeter in comparison to a lysimeter? Because methodologically, it is the most. It seems that it is most accurate to the as the correlation to the soil moisture, because it's a matter of real water content, because it's weighing the variation of the content. And second, if you are using, for example, multiple sensors at different depths, such as every 15 centimeters, for example, will there be a cross effect between the sensors due to high frequency measurement technique, or will you switch them one by one? What is the effective measurement area for each sensor, in other words? But
they're on 2.2 gigahertz, they don't have the effect one to another, especially that they are on different depths that are far apart. So for example, 5, 30, and 60 centimeters surrounded by the soil. We didn't notice any interference on that. And we have compared that with other sensors, as I said, with the stability with respect to different soil types is obvious, with the same accuracy that you would get from Decagon, for example.
Why I asked is because, you know, it's after embedding it, burying it inside the water, its coverage and the surface integration is very important, and it must be, for example, measuring some certain area, not very small percentage, so that it can reflect the average around the sensor. So, for example, does it reflect the measurement of the water content around 5 centimeter or 10 centimeter range? Otherwise, you know, there might have been also some spots in the soil. It is usually required not to be so large, not to be so small in millimeter level. So the sensitive area is also important. And how is the sensitive? How does the sensitive area change around the sensor?
Yes, good question. We have so-called porous matrix on the sensor made of ceramics that is basically it's based on nanotechnology that is give us the possibility to control the radius of based on the water pressure, how it will affect how far from the sensors it will take the absorption of water to detect the measurement. If we go in a too narrow thing, we will get local measurement that might not be accurate with respect to surroundings. If we go too far, we will have the interference with the other things. So based on the size of the porous matrix and nanostructure, we can control the radius where we are taking the measurement.
Okay. Dr. Ömer Vanlı has a question. Ömer, are you able to hear us?
Yes, thank you. Firstly, for your presenting. I just wanted that as a crop modeling expert, I just wanted that, do you have any collaboration with crop modeling expert for using all of these data and evaluate data in the modeling?
Yes, we have that, but I must say that the crop modeling people are kind of very strict and old-fashioned. When we talk to them, they don't accept the technology easily in this. When we show them that with AI and with new neural networks or random forest or whatever, we can go somewhere, they are reluctant to that, and they are saying, no, it should be taken in a different way. But we are talking about cooperation with serious institutions. I wouldn't give their name now, but the top global institutions, and we have to go into really. We see over the years how the ice is melting, and they are accepting new things to go there. And yes, we do work on them, but I think that it's still a long way to go in the future.
Okay, thank you.
Yes, for the point of data analytics, in fact, there are two important things that increase the nonlinearity. The first is the variety of the seed, because wheat is not always wheat. There are hundreds of types of variety, and the model parameters always change dramatically. And the second is the phenological stage, and for each phenological stage, it is a different system. So the combination between the seed variety and the phenological stage, in fact, pushes the real application towards a sort of marriage between the data science approach and the model parameters. So model parameters can be a prior information, or model parameters can also be driven through data analytics. So we cannot say that it is easy to apply data analytics for real-time, depending on different cases, because the scale is also important. When we are talking the scale, if it is parcel or a region, so decisions also are based on different models depending on the scale. So models are important for initiating the even the machine learning or data analytics based process for the farming decisions. So it's a real issue. So thank you for your participation all. And Vladimir, we are always happy to see your presentations, and you are always welcome. They are quite valuable. And we also congratulate your team about their sustainable, continuous creativity on finding the solutions for agricultural production and the biosensing for the system. So thank you for your all participation to ISAM webinar, and we are also expecting you to participate again 8 weeks later on March. So I will be sharing the relevant information about the next presentation of ours. Thank you, and hope to see you in the next one.
Thank you. Bye.
Bye-bye.